Okay, in this video we're going to start section 7.4. The section covers arc lengths and surfaces of revolution. In this video we're just going to do the first bullet point, the arc length of a smooth curve. In the next video we will find the surface, the area of a surface of revolution. So arc length. In this section, definite integrals are used to find the arc length of curves and the areas of surfaces of revolution. In either case, an arc, or a segment of a curve, is approximated by straight line segments whose lengths are given by the good old distance formula. A rectifiable curve is one that has finite arc length. And you will see that a sufficient condition for the graph of a function f to be rectifiable between 2 points is that the derivative f prime must be continuous across the interval. Such a function is continuously differentiable on the interval from a to b, and its graph on the interval from a to b is also a smooth curve. And here's the technical part of it. We are taking an arc. Here we have a nice curve, downward opening parabola, and we're picking points and we're finding the distance between them using the distance formula. And of course, if we only have a few points that we use, it's not going to be a very good approximation. But as we, chop this arc up into smaller and smaller pieces and find the distance between them with the distance formula, our approximation becomes better and better. So eventually, we have our summation notation. We're going to let our norm approach 0. The largest of those chunks is going to be getting smaller and smaller and smaller. So we're going to chop our curve up into infinitely many, infinitely small pieces using the distance formula and sum up all those little lengths. And when we do that, here is our summation notation. We wind up with this definite integral. The integral from a to b, and we have a radical. Underneath the radical is 1 plus a quantity squared. And what that quantity squared is the derivative, f prime of x. So find the derivative, put it under a radical quantity squared with a plus 1 in front of it, and that's under a radical, and we integrate from the left endpoint to the right endpoint. Seems simple enough. So here's the official book definition. The top one is if we have our function in terms of x. The bottom one is if our function is in terms of y. So we integrate from the left to right endpoint. Again, under the radical we have a 1 plus our derivative quantity squared. Dx if we're with respect to x, dy if we are written in terms of y. And that is our arc length, denoted by the variable s. S equals those integrals. So let's check out example 1. Find the arc length of the graph of. Here's our function. Y equals 1/6 x to the third plus 1 over 2x. And we want to find the arc length from the interval 1/2 to 2, as we see in the picture. Here's our graph. It's sort of parabolic in shape. Our left endpoint is at 1/2. Our right endpoint is at 2. We're going to find the exact length of this curve if we were able to straighten it out and measure it with a ruler. So our formula, part of our formula is, where is that? We need the derivative. We need the derivative under that radical quantity squared. So here is my function. I'm going to do different notation here. F of x equals instead of y equals. And this is 1/6 x to the third plus 1/2. And I'll rewrite that with a negative exponent. 1/2 x to the negative 1. And I need the derivative. F prime of x equals, well, this would be 3/6 x squared, or 1/2 x squared, minus, that negative 1 will come down, minus 1/2 x to the negative 2 power. And I could, instead of writing that as 1/2 x to the negative 2, I can just put my x in the bottom and make it a positive x squared. And from here I'm going to factor out a 1/2. F prime of x is 1/2 times the quantity x squared minus 1 over x squared. So there's my derivative. I'm going to move some of this stuff up here. Move my derivative up. We will need that shortly when we start plugging stuff into our new formula. So our arc length formula is s equals the definite integral from a to b of, and we have a radical. Under the radical is 1 plus a quantity squared, and what that quantity is is our derivative, f prime of x. So let's plug in the numbers from our problem. Lower and upper limits, a and b, for us is 1/2 to 2. And then we have our radical, and 1 plus a quantity squared. And our quantity squared is 1/2 times the quantity, x squared, or 1/2 times the quantity x squared minus 1 over x squared. So the setup is done. The calculus idea is simple. If we solve the antiderivative, we have the arc length. Now it comes down to algebra skills. How well can we FOIL stuff out and condense and factor? So we have a little bit of work here. Integral from 1/2 to 2. We are going to FOIL out what is under there. So distribute the squared power. 1/2 squared is 1/4. And now we're going to square this quantity. Square the binomial, so it's going to be x to the 4th minus. Our middle term is 2 times our two given terms multiplied together. Well, nice here, if I multiply these, I get x squared over x squared, or 1 times 2 is 2. And then plus 1 over x to the 4th power. Alright, next we're going to distribute that 1/4 and combine any like terms. So we have our integral from 1/2 to 2. 1 plus, distribute the 1/4, a quarter x squared. 1/4 times -2 is -1/2. Quarter times our last term is 1/4. And I'm going to write it this way, 1 over x to the 4th. To combine like terms, we only have 2. Oops. Why did I do that? This is not x squared, it's x to the 4th power. Alright, the only terms to combine are the 1 and the minus 1/2. 1 minus 1/2 is positive 1/2. So our integral goes from 1/2 to 2. Big radical. 1 plus, oops, no. 1/4 x to the 4th. The 1 minus 1/2 is now a plus 1/2 plus 1/4 times 1 over x to the 4th power. And dx. So I've combined my like terms, and now, we're under a radical. The only way to get out from under a radical is if we have a quantity squared underneath the radical. So let's see if I can get some squared quantities under there. Well, first, let's factor out a 1/4. Factor out a 4th. If we factor out that 4th, we're going to be left with x to the 4th plus, how many quarters are in a half? Well, there's 2 of them, plus 1 over x to the 4th dx. So can I condense any of that into quantities squared? Well, 1/4, that's a quantity squared. That's 1/2 squared. And let's see, now I can factor this down kind of like it was when we started, but just with a sign change. That quantity would be x squared plus 1 over x squared. And that would be a quantity squared. And let me make my radical just a little bit longer, make sure that 2 is under it. And there we go. Any quantity under the radical that is a quantity squared, we can bring out. Oops. So we have our integral from 1/2 to 2. And let's see what escaped. The 1/2 quantity squared gets out as a plain old 1/2. And the square and the square root cancel. This quantity squared and the radical collide and undo each other. And we're left with what's under it. And I almost forgot my dx again. There we go. So we have our antiderivative. We could, factor this 1/2 out front by the constant multiple rule. And now we have 2 terms, and we're ready to just integrate those. So we're going to have our 1/2 integral from 1/2 to 2 of x squared plus x to the negative 2 dx. So the algebra work paid off. We've simplified our function quite nicely, and we'll be able to take an antiderivative, no problem. So 1/2 raise the power by 1, divide by the new power, x to the third over 3, plus raise the power by 1, divide by the new power. That's going to be x to the negative 1 divided by negative 1. So that's going to become minus 1 over x. And we evaluate from 1/2 to 2. So the worst part of this antiderivative is going to be that little 1/2 as our lower limit, but that won't be too bad. Let's see here. Plug in the 2 first. 2 goes in. We're going to get 8/3 minus the 2 goes in for this x. 8/3 minus 1/2. Minus. Plug in the 1/2. 1/2 to the third is 1/8. 1/8 divided by, well, let's see here. That is going to be 1/8 divided by 3, or times its reciprocal, times 1/3. So here we're going to have an 1/8 times a third. And then minus, we plug the 1/2 in here. 1 over 1/2 multiplied by the reciprocal. That'll turn into a 2. And when we work in here, we combine, get common denominators, collect up any like terms. We're going to get 33/16. That is our arc length. Bring the picture back down. That is the arc length from this point to this point. If we are going along and measuring that as we go, it's going to be exactly 33/16 units. Okay, that was a pretty juicy problem there. Next example isn't so long. Example 2, again, just another arc length. Find the arc length of the graph of, here's our function, y minus 1 quantity to the third equals x squared on the interval from 0 to 8, as shown in the picture. So let's see here. Let's first solve for x. So if we square root each side, we're going to get x equals plus or minus the square root of the quantity y minus 1 to the third power. Or because we're only here in the first quadrant, we can disregard the negative root and just hang with the positive one, and we can rewrite that as a rational exponent, y minus 1 quantity to the 3/2 power. So there's our function, x equals y minus 1 quantity to the 3/2. We are going to need the derivative. Let's see here. Let's change up our notation. dy dx, or dx dy, the derivative of x with respect to y, equals, bring our power down, 3/2 quantity y minus 1 to 1 power lower, and that power would just be the 1/2 power. And then chain rule would say our inner function's derivative. Our inner function is just y minus 1. That derivative is 1. So here is our function's derivative. That is going to go under the radical and be a quantity squared. Oops. And I'll get this out of the way here. So our formula is the arc length S equals the integral from C to D, because this time we are with respect to y now. In that formula they did use C and D there, of radical 1 plus our derivative dx dy, that derivative quantity squared dy. Oops. And let's plug in the numbers relevant to our problem. So we are integrating, and we're integrating with respect to y. So as we look at the y-axis, our our function starts here. It's going to end up here. So we are integrating on the y-axis from 1 to 5. And then we have our radical. And then 1 plus, and we're going to plug our derivative in here and quantity square that. And I did move the derivative out of the way, but that was 3/2 quantity y minus 1 to the 1/2 power dy. Oops. So let's work under that radical and try to simplify some stuff here. Our 1 plus. Let's see, if we distribute the squared, that's going to become 9/4. 9/4, and then the square and the 1/2 power are going to collide, and that's just going to become y minus 1. Y minus 1. So we distribute the 9/4. Integral 1 to 5. 1 plus 9/4 y minus 9/4 dy. And we can combine. We have a 1 and a minus 9/4. So 1 is like 4/4. So we have a 4/4 minus 9/4, which is a negative 5/4. So under that radical, we're going to have 9/4 y minus 5/4 dy. And we're integrating from 1 to 5. So let's see, what can we do next underneath that radical? Well, it looks like we can factor out a 1/4. So we're going to have our integral from 1 to 5. Here we're going to have a 1/4 times the quantity, 9y minus 5 under the radical. And that 1/4 we could write as 1/2 squared, or the square root of 1/4 is a half. So we can pull that half out in front of our integral sign from 1 to 5. And then we're going to have this quantity left under the radical. And let's write that as 9y minus 5 to the 1/2 power dy. Because it looks like we're getting close. We can integrate now, I do believe. Or we're pretty close. We are going to have to tweak it with a constant. So think inner function. Here is the inner function 9y minus 5. What is the derivative of the inner function? Well, that's going to be a 9. So I'm going to need to multiply by a 9 to get my du. And to balance that, I will need a 1/9 out front with the 1/2. So here out front we are going to have a 1/18. And now we're ready to integrate. We have our inner function u, we have our du, 9 dy, and we have our exponent is 1/2. So when we take the antiderivative, it's going to be that same quantity, that 9y minus 5. We're going to raise the power by 1 to the 3/2 power, divide by that new power 3/2, which is the same thing as multiplying by 2/3, the reciprocal. And I almost forgot my bracket. We are integrating that from 1 to 5. Okay. See, we have our 1 over 18 times 2 over 3. We can sort of cancel on the diagonal. That'll reduce to a 1 and a 9. So we're going to have 1/27, and then our 9y minus 5 to the 3/2 power. And we're ready to evaluate. So 1/27th, plug in the upper limit 5. 9 times 5 is 45, minus 5 is 40 to the 3/2 power. Minus, plug in the lower limit. We plug in the lower limit of 1. 9 times 1 is 9, minus 5 is 4. 4 to the 3/2 power. And close the bracket. Plug that into the calculator, and we get approximately 9.073. Again, that is our arc length. How far is it from this point at 0,1 to this point at 8,5, traveling across our function? Pretty close to 9.073 units. Example 3. More arc length. This time we're going to have a little more fun with a natural log of a cosine function. Natural log of the cos of x. So, find the arc length of the graph of y equals the natural log of the cos of x from 0 to 1/4 pi, as shown in the figure. So we're starting at the origin, going to an x value of 1/4 pi. How long is that piece of the function? So, our function is y equals natural log of the cos of x. So we need the derivative, dy dx. Well, the derivative of the natural log of something is 1 over that something, 1 over the cos of x, times the derivative of what we were taking the natural log of. The derivative of cosine is negative sine x. And we could combine that and get negative sine x over the cos of x, which is equal to the negative tangent of x, negative tan x. So dy dx equals negative tan x. And we're going to plug that into our new formula. And we are integrating here from 0 to 1/4 pi. And our formula says there's a radical, and under that radical is 1 plus our negative tan of x quantity squared dx. And of course, negative tangent times negative tangent is positive tangent squared. So under our radical, we have 1 plus tan squared. 1 plus the tangent of x squared, tan squared of x. Well, we have some trig identities. 1 plus tan squared is one of our Pythagorean identities. And the 1 plus tan squared is equal to secant squared. Secant squared of x. And look at that. We have a radical with a squared term under it. And that radical and the squared will cancel each other out. So our integral's getting pretty simple. From 0 to 1/4 pi. Secant of x dx. Well, what's the antiderivative of secant? Well, that is the natural log of the absolute value of secant of x plus tan of x. Absolute value, and we integrate that from 0 to 1/4 pi. So, if we plug in our upper limit, the natural log of secant of 1/4 pi plus tan of 1/4 pi minus the natural log of the absolute value of the secant of 0 plus the tan of 0. And now we have to think back to the good old unit circle. The ln of absolute value, secant of 1/4 pi. Well, that's the reciprocal of that is the reciprocal of cos of 1/4 pi. Cos at 1/4 pi is square root of 2 over 2. So secant of 1/4 pi is 2 over the root of 2. And if we rationalize that denominator, if we rationalize the denominator, we're going to get 2 square roots of 2 over 2, or just the plain old square root of 2, plus the tan at 1/4 pi is 1, and then minus the natural log of the secant of 0. Again, secant is the reciprocal of cosine at that point, so that's going to be a 1, plus the tangent at 0 is 0. So I guess we can drop the absolute value bars now. We could have actually dropped them in that last step, because we are dealing with positive quantities, and we know that for sure now. So we're going to have the natural log of the quantity, square root of 2 plus 1, minus the natural log of 1, and the natural log of 1 is 0. So that goes away, and we just have to do the root of 2 plus 1 and take the natural log of that, and we get approximately 0.881 units. Alrighty. Example 4, nothing to write down here, but this is a neat real-life application. Where would you ever use something like this in the real world? If we're stringing cables, the length of a cable. An electric cable is hung between 2 towers. The towers are 200 feet apart, as shown in the figure. So here's our, they're imposing a coordinate axis on there and putting the y-axis right in between the towers. So we're going from negative 100 to plus 100, and we have this cable, hanging down in between the 2 towers. So, gravity's pulling down on that cable, and the cable takes the shape of a catenary, whose equation is y equals 7/5 times the quantity e to the x divided by 150 power, plus e to the negative x divided by 150 power, and that's equal to the 150 times the cosh of x divided by 150. Find the arc length of the cable between the towers. So, here is our derivative, and we plug that into the formula, square it. We go through all these advanced, complicated, or complex computations, and we take the antiderivative and get approximately 215 feet. So maybe someday you'll be working for a company and you're stringing power lines across the entire United States. They're going to want to know roughly, or pretty close to exact, how much cable would you need to go from East Coast to West Coast if you have towers spaced so far apart and you have your cable, of course, bowing down because of gravity. And the first 4 examples were all the length of an arc. In the next video, we'll pick up with example 5 and do surfaces of revolution.